Hi everyone, my name is Samuel. Today I'm going to talk about the Clausius Clapeyron equation in physical chemistry. And this is the equation, right, I'm talking about, right, which actually relates, right, the vapor pressures and the temperatures, right, for boiling liquids. In this equation, right, this equation says, right, the ln, right, the natural logarithm of the ratio of the P1 and P2. You know, P1 and P2 are the vapor pressures at the temperature T1 and T2 correspondingly. That equals to here the enthalpy of vaporization over the gas constant times the 1 over T2, right, minus 1 over T1. Now, in this lecture, I will spend most of the time discussing how this equation is derived. And before I do that, let me mention when this equation holds. Now, this equation only holds at the equilibrium condition of a boiling liquid. That occurs when the boiling, the equilibrium condition occurs when the boiling happens at the surrounding temperature, which is equal to the boiling temperature of the liquid. That means the Gibbs free energy change is zero. It doesn't hold. This equation doesn't hold when the boiling of a liquid occurs at the surrounding temperature greater than the boiling temperature of the liquid. Definitely in which the Gibbs free energy change is less than zero. That means this is the spontaneous condition. Okay. Now, let me start talking about the derivation of the formula, how this formula is derived. Now let's consider, right, the boiling process of a certain substance. The substance A, right, definitely is at equilibrium, right? That's when the formula, that equation, right, the equation holds only. Definitely during the equilibrium, right, the Gibbs free energy change, right, of the process is zero, which means the Gibbs free energy, right, of the liquid, right, equals to that of the gas, right. And if we take the differential, right, of this expression, right, we can get this, right, dg the liquid, right, equals to dg of gas. And recall we have learned, right, the Maxwell equation, which relates the differential of the Gibbs free energy to the temperature and the vapor pressure. Right? And this equation, right, is Gibbs free energy, the differential of Gibbs free energy, dg equals to negative of entropy of a substance times dt plus the volume times the dp. Notice the p here is the vapor pressure, in this equation. Right? And when we plot the Maxwell equation to this expression, right, dgl equals dgg, we can get the negative of the entropy of the liquid phase of the substance, right, times dt plus the volume of the liquid, right, times dp. That equals to negative of the entropy of the gas times dt plus the volume of the gas phase, right, times dp. Now if we process this equation, we will get the entropy of the gas minus the entropy of the liquid. Use the difference multiplied by the dt. That equals to the volume of the gas minus the volume of the liquid. Use that difference to multiply by dp. While now we have to assume, right, the ideal gas behavior for the gas phase. We know the intermolecular distance, right, of the gas phase should be much bigger than that of the intermolecular distance of the ideal gas should be much bigger than that of the liquid, right? Therefore, we can actually neglect the volume of the liquid when we compare that to the volume of the gas. That means this term, right, the volume of liquid can be treated as 0. So this expression on the right hand side can be approximately equal to the volume of the gas times dP. Now we apply the ideal gas equation, right? So that's the volume of gas would be equal to the nRT over the P, and that multiplied by the dP. Now, so we have successfully processed the right hand side, right, of the right hand side expression. How about the left hand side expression? Some students may get stuck, right, in it. How do we process it? Now here's the strategy. We know, right, during again equilibrium, right, the Gibbs free energy, right, of the liquid equals to that, right, of the gas, right. And remember, right, the Gibbs free energy is equal to the enthalpy H minus the T, temperature, times the entropy, right? And if we plot that equation, right, to this expression, we'll get the enthalpy of the liquid phase minus the temperature times the entropy, right, of the liquid phase equals to the enthalpy of the gas phase minus the temperature times the entropy of the gas phase. And if we again process this equation, we will get the temperature, right, definitely in Kelvin, times the entropy of the gas phase minus the entropy of the liquid phase. That equals to the enthalpy of the gas phase minus the enthalpy of the liquid phase. Now definitely this would be equals to the N, right, the number of moles, multiplied by the heat of vaporization, right, whose unit, right, is joule per mole, right. So we can actually now isolate this term, the Sg minus Sl, which is, so this term is actually equal to the N times the enthalpy of vaporization over the T, right? Move the T to the other side and block this term, I block this expression, right, back to here, right? We get the N, right, times delta, this heat of vaporization, right, over the T times what dt, right, equals to, again, on the right hand side would be nRT, right, over P, right, times dP. Now actually notice, right, we can cancel the terms, right, the N, right, so we get the enthalpy change, the heat of vaporization over T times dt equals to RT over P times dP. Now the rest, right, is a piece of cake, right? We just solve this differential equation, right? What we can do is we move all the terms, right, with T, right, and all the terms with the P to each side, and we get the enthalpy, right, of vaporization over the T square, right, times dt, equals to R over P, right, times dP. And then we take the integral on both sides. Right? So take the integral of temperature, right, from T1 to T2, right, and then we take the integral of the pressure from P1 to P2, right, and definitely, right, we can assume the heat of vaporization, right, is constant, right, over a pretty small range of temperature. So we can take this out of the integral, right? Okay. Now after we process, right, this different this integral we can get at the final, right, equation form, which is the enthalpy change. I'm sorry, the heat of vaporization, right, times 1 over T1 minus 1 over T2. That equals to the R, the gas constant, times Ln of the ratio, right, of P2, the vapor pressure P2 to P1. Okay, thank you for watching, and I hope this video helped you guys with your studies in physical chemistry. Hope you enjoy it.